Okay, internal flows. Internal flows are super useful for us in chemical engineering, petroleum engineering, and of course also for us in materials engineering. Uh, they for bank they are based on the same concepts we have already seen, but they have one new interesting thing that that will be what makes all the difference. So internal flows. Here we have a schematic that is from the book of flow getting into a pipe. And look at this, and this is why we discuss boundary layers and it helps us so much. As the flow is coming into the pipe, the flow was flowing freely before getting into the pipe, and as it touches the lip of the pipe, the entry of the pipe, we're going to have the no-slip boundary condition. And the fluid in touch with the pipe kind of gets stuck and starts to develop a boundary layer. So if this is a pipe and this is a flow coming into the pipe, we start to develop a boundary layer. At the very beginning, the boundary layer is very thin. The flow doesn't even know there is a pipe. All the fluid knows is that it cannot move here and there is some sort of free stream up here, and starts to build this boundary layer. If this was a flat plate, who cares? We already discussed and it's not a problem. And the boundary layer would keep growing and growing and growing until it becomes a turbulent boundary layer, and then it keeps growing and growing and growing to the point in which we can have geological boundary layers in the atmosphere, right? But guess what? In a pipe, that doesn't happen because the boundary layer grows and grows and grows. But on the other side of the pipe, and that's why it's an internal flow, you have an opposite side. You also have a boundary layer that is growing and growing and growing. It gets to a point at which they cannot keep growing because they impinge on each other. This is the whole concept of entry length, which you very likely heard in fluid mechanics. So at the beginning, we develop a boundary layer, and that regime is called the entry length, And when the two boundary layers collide, you have what is called the fully developed region. And of course, it's not super sharp. It's kind of like everything about convection. There is a little range. But for the purpose of this class, we're going to discuss them as if they were sharp. The entry region in which we develop the boundary layers, and the fully developed region in which there is no boundary layer anymore, and we have a profile that is a velocity profile that is going to be kept constant downstream. In a pipe, we tend to know the flow we have, right? Like the flow in kilograms per second or cubic meters per second. And we know that the velocity against the walls is zero because of the no-slip condition. And the velocity in the middle obviously is not zero, is bigger. And we have a profile. When we talk about flow, the velocity of flow in a pipe, what we're going to be discussing is a term of average velocity, this UN. This is the average velocity inside the pipe. Because there's a zero velocity on the surface, it's a maximum velocity in the center, but in the end, the one that helps us make sense out of things, every time we talked about previous problems in this class, in which I was coy and I didn't make any nuance, every time we said so many cubic meters per second or so many kilograms per second, we translated that into a velocity. But it's more subtle than that, right? Because we have a velocity range. So these velocities we're talking about, and the ones I've been talking about before, were this mean velocity, this average velocity. For the case of a laminar flow, You can look at the book, but you do the math and you come that the maximum velocity is 2 times the average, right? This is the maximum. The average cannot be the maximum, right? And of course, it's somewhere between maximum and 0. It is the mathematical truth. Our very fortunate mathematical truth is that the average velocity is half the maximum, which is going to be good to use later. The flow inside the pipe can be just like outside, can be laminar or can be turbulent. This is fluid mechanics. I'm not even getting into heat transfer yet. And how do we know if it is laminar or turbulent? Based on a critical Reynolds number. So it is laminar up to 2300 Reynolds. That is based on the diameter. And is fully turbulent at 10,000. And we have a range of transition. And guess what we're gonna do in this class? We're gonna pretend that as at the end of laminar, we go full in turbulence. Acknowledging that really we have a range in which we have a transition between laminar and turbulent. But we're gonna say laminar up to 2300, and from 2300 onward, we're gonna call it turbulent. So something that you will be asked on Monday is the flow laminar or turbulent in this pipe? And you're gonna go and check out if it is more or less than 2300. The Reynolds. So something cool that the book does not do, but I found it so useful, is they don't say what gives the hydrodynamic entry length. They just say this formula is to calculate. But we can calculate it, and I want to do this with you. And it's this way. Let's talk about the hydrodynamic entry length. That is the entry length for developing the flow. We're not talking about temperatures here. And we had said that a boundary layer develops until the two boundary layers collapse. So at this point in which we have the entry length, we can say that the thickness of the boundary layer is more or less half a diameter of the pipe, right? I will say that. Also, I'm gonna say that in this boundary layer, the free flow velocity is more or less the maximum velocity in the pipe, that is 2 times the average, right? This is an approximation, but with the maximum velocity, I'm gonna say that the free flow as the two boundary layers are about to collide, the free flow is 2 times the average. So I would say the thickness of the viscous boundary layer is half a diameter. What I put here, the thickness was 3, and this 3, remember, it's not just a 3, it's 4 years that ruined the life of Blasius, just so you can have a number 3, and you don't need to ruin your 4 years in getting it. This is not just any number 3, right? Square root of nu x over velocity, and x is going to be the entry length that I'm using the notation of the book, which is pretty cumbersome. That is x fd from fully developed h. H means hydrodynamic, right? And what velocity we decided to use? 2 times the average velocity, because it's the maximum, right? That's the maximum velocity. If I solve for this, right? If I solve for this, I get that the entry length, xfdh, what a name, the entry length divided the diameter is 0.055 Reynolds diameter. We did this together. You want to see what the book says? The book gives you, without any explanation, it just says, the word of God is 0.05, but we did it together, 0.055. I am feeling good about this. So at the very least, it means that we understand where the entry length comes from. what it is, right? And we understand it well enough that we can rederive this thing that who knows where it comes from because the book didn't tell us. This is among the things that will be on Monday. On Monday, the exam will start with, will include transient conduction, which is what we saw 2 weeks ago. Will include boundary layers and external flows, and internal flows as we see now. What is the entry length for a turbulent flow? In the case of turbulent, things change. And I don't really know where this comes from, but I'm taking the book and I couldn't do anything better. It says that the fluid is fully turbulent. The entry length in turbulent flow is between 10 and 60 diameters. In this class, we're going to be using 10 diameters. So what is the entry length when the fluid is coming turbulent? 10 diameters. And that means a turbulent boundary layer is developing until it collides with the other turbulent boundary layer on the other side. And from then on, we have a fully developed turbulent flow. And that distance is 10 diameters. Thermal entry length, right? Now it's interesting because we have a fluid entry length, right? Hydrodynamic entry length, but also we have a thermal entry length because the two boundary layers are not the same. And let's talk about entry length on pipes that carry water, oil, and air, right? And let's leave like pipes with molten sodium for somebody else, which we could also do, but we choose not to. So what are we going to do? Same thing, see where the two boundary layers collide, but in this case would be the two thermal boundary layers. There is something interesting here because in this case, the external flow, right? Let's see if I have a better schematic here. No, I don't. Okay. So we said that for oil, water, and air, the boundary layer, the viscous boundary layer is thicker than the thermal boundary layer, which means most of the development of the thermal boundary layer is in fully developed flow. Because the two boundary layers that are hydrodynamic, the viscous boundary layer, are very thick and collide with each other very soon. And the thermal boundary layers keep flowing downstream in fully developed flow, right? Until those two collapse. So we can do a similar analysis as we did before, that the thickness of the thermal boundary layer is half a diameter. We're going to use the same 3 to account for the gradients, right? And when we calculate this, we end up with 0.055, right? But also appears a Prandtl here. And the Prandtl is the ratio between the kinematic viscosity and the thermal diffusivity. And guess what the book says? Instead of 0.055 Reynolds Prandtl, says 0.05 Reynolds Prandtl. That means we understand it. That means we know what we're doing. In addition, we can plug and check and calculate it. So this is as far as the quiz is going to go on Monday. I'm going to stop here, and we're gonna have office hours at 2, as usual, for anybody who wishes to join. Thank you very much. Let's stop here.